Hello everybody, hope you're doing well and thanks for joining us for another video, which today is going to be addressing Coriolis deflection caused by Earth's rotation. Now, there is seemingly quite a common misconception about this, particularly amongst flat earthers, who argue that the Earth can't be rotating and that Coriolis isn't a real thing, because then if you launched yourself straight up in a hot air balloon, hovered in the air for a while, the Earth would turn underneath you, and when you came back down again, you'd be in a completely different location.
So the Earth has to be spinning at 1,000 miles an hour, right? And this plane was going across India in the middle of the night. I could plainly see the cities, and they were completely still. The plane was going at probably between 800 and 850 miles an hour. And it was a beautiful, clear night. I could see clearly that the cities of India, which is over the equator approximately, were completely still.
They say airplanes consider the Coriolis effect, but pilots never consider a Coriolis effect. They just don't.
Tools on planes don't account for illusions, you idiot.
It's you're claiming it's an illusion, not me.
No, it is an illusion. I understand the Coriolis effect definition.
Now, the first thing we need to nail down for this is Newton's laws of motion. An object in motion will remain in motion unless it's acted on by another force. For example, if you're on a train that's moving at 50 meters per second, both you and the train are traveling at that same speed, but because you're sitting still, then your speed relative to the train is zero. Now, if you were to have a ball in your hand, that ball would also be traveling at 50 meters per second with you and with the train. If you throw the ball up in the air, it's still traveling 50 meters per second in that direction because there's no force acting on it horizontally that would cause its speed to change. The only forces acting on it are vertically, so it will go up and it will come back down, but it will land in the same spot relative to you. If you were to hold the ball out of the window and throw it up, then there would be a force acting on it due to the air that is not moving at the same speed as the train. That would slow the ball down, and to you, it would appear to travel backwards. Though in reality, it would still be traveling forwards, just not as fast as you and the train. If the train had a tailwind of an equal 50 meters per second, you wouldn't want to be someone stood outside, that's for sure, but the ball would then land back in your hand because the air would be moving at the same relative speed to the train, so there would be no longer a force acting on the ball to change its horizontal velocity. I kind of demonstrated this back in December because on our flight from Chile to Antarctica, it was pretty much empty. We basically had the entire cabin to ourselves and we were free to move around as we pleased. So MC Toon recorded me whilst we were cruising at more than 500 miles an hour, and I jumped in the air and landed right back in the same spot where I started. Because let's say the plane was traveling at 500 miles an hour just before I jumped, I was also traveling at that 500 miles an hour. So once I left contact with the plane, I was still traveling at that same 500 miles an hour. If I'd jumped out of the plane and there was no air resistance, my horizontal velocity would remain at that same 500 miles an hour as the plane. So I would fall to the ground, but I would stay directly underneath the plane the entire time. In reality, that doesn't happen because air resistance immediately starts to slow down that horizontal velocity, so I wouldn't land directly underneath the plane, but I also wouldn't land directly straight down from wherever I jumped out either. That's why military planes drop bombs before they get over a target, but the plane has already gone past the target before the bombs hit the ground. So how does this tie into Coriolis, you might be thinking? Well, the idea that a hot air balloon could take off and come straight back down in a different country due to Earth's rotation is flawed because the balloon is moving at the same speed of the Earth before it takes off. You'll often hear flat earthers talk about the globe rotating at 1,000 miles an hour, which is specifically the tangential speed at the equator. The Earth rotates once in 24 hours. The circumference of the Earth is approximately 24,000 miles. So 24,000 miles an hour in 24 hours is about 1,000 miles per hour. But at the poles, it still rotates once in 24 hours, but the circumference is almost zero. Therefore, the tangential speed is almost zero as well, which is going to be important shortly. But first, let's say this hot air balloon is being launched at the equator. Before it takes off, it will be rotating at the same 1,000 miles an hour as the globe. So when it then lifts off the ground, it's still traveling at that same 1,000 miles per hour because there's no force causing the speed to change. No different than if you were to launch a tiny balloon inside a moving train. So no, the balloon going straight up and coming straight back down would not experience the entire Earth rotating at 1,000 miles an hour underneath it. Technically, you do get a slight drift, but nothing close to 1,000 miles an hour that flat earthers think. Now, let's say globe has a radius of 3959 miles. That gives us a circumference of 24,875 miles, which equals 1,036.4583 miles per hour. So the balloon at launch would be traveling at that same 1,036.4583 miles an hour. We'll ignore other factors like wind affecting the balloon, but if the balloon rises to about 5,200 feet, that's 1 mile above the Earth, which now means it would be 3,960 miles above the center of the Earth, which would make the circumference of that balloon's path 24,881 miles, so about 6 miles further to complete one full loop. Well, to do that would require a speed of 1,036.7083 miles an hour, but the balloon is traveling a quarter of a mile an hour slower than that. So if you launched a balloon straight up to 5,200 feet, held it there for 1 whole hour, and descended it straight back down, you'd find yourself a quarter of a mile from the location where you took off from. A quarter of a mile in 1 hour is a quarter of a mile an hour, or 0.11 meters per second. The average wind speed in the UK in 2023 was 4.3 meters per second. So the Coriolis effect on a hot air balloon would be about 40 times less than the effect that the wind had on the balloon. As for flight times, they hit the same basic problem. If you have two planes at an airport on the equator, one takes off and flies west and the other takes off and flies east, some flat earthers argue that the time taken to travel a given distance would vary drastically between those two planes because of Earth's rotation. Except both planes would already be going that 1,000 mile an hour tangential speed of the Earth before they took off. So if both planes flew at 500 miles an hour, then after 1 hour, both planes have still travelled 500 miles, regardless of if they're going east or west. Where Earth's rotation does start to play a factor, though, isn't travelling east to west, but rather north to south. Because as we've already covered, the tangential speed of the globe at the equator is about 1,000 miles an hour, but at either pole, it's zero. And so everywhere in between those locations will have a tangential speed somewhere in between, depending on the distance around that particular latitude. So where the latitude distance is, say, 12,000 miles, then the tangential speed would be about 500 miles per hour. So if a helicopter is on the equator and it flies straight up and holds altitude for a period and then comes back down, as we've already covered, Earth's rotation would have basically no impact, because the helicopter has that 1,000 mile an hour speed of the Earth already. However, if the helicopter begins flying straight north or straight south, it's still conserving that 1,000 mile an hour tangential speed from the Earth from where it left the ground, but it's now flying over an area of Earth that isn't traveling at 1,000 miles an hour. So even if it continues in the same direction, the path it would trace on Earth would cause a curve. And this is basically Coriolis. The fact that when traveling north or south, you're beginning with the tangential speed of your starting location, but you're moving over a part of Earth with a different tangential speed. And this varies depending on which way you're traveling in which hemisphere. If you're at a high latitude in the north, then flying south you're starting with a smaller tangential speed and moving to an area of Earth that has a higher tangential speed, so it will give the appearance that the plane is drifting to the right. But if you start at the equator and still fly south, you're then moving to a region with a lower tangential speed than your starting velocity, so your plane would be appearing to drift to the left. And this does impact things like flights. For example, I purchased this book called Global Navigation for Pilots, and from page 279, it talks about the inertial reference system of an aircraft, how it has to align itself to a plane's latitude before takeoff, and then includes corrections for Earth's rotation into its systems as they fly. For planes without that sort of a system, then flying directly north or south would have a very gradual drift. However, the problem with looking at this for planes is a plane is constantly receiving adjustments from the pilots, and they're following a planned route. So any subtle drift beginning to show will appear as the plane moving off its intended flight path, and the pilot would correct for it. But as we've already covered, the deflection rate of Coriolis is only a fraction of that of wind. So while both wind and Coriolis have an impact on the plane, the effect of the wind is much more noticeable than any drift that's constantly needing to be corrected for. Where Coriolis is more of a prominent issue is with anything unguided, because while a plane can correct for Coriolis gradually throughout its flight, an unguided projectile can't. So all corrections have to be applied before that projectile is fired. For example, people will often talk about snipers, given they obviously need very high levels of accuracy.
They say snipers take Coriolis into effect, right? But then the actual sniper never takes Coriolis into effect.
However, the bullets fly at such a high speed over a relatively short distance that the bullet's flight time is only a couple of seconds. So the impact of Coriolis is pretty minimal, apart from when you're shooting at very, very long ranges, which snipers say they do have to then account for Coriolis.
And go out and try to return the same data, let's say a week later. And one of the common issues that we see is the Coriolis effect. And what guys are not doing is taking into account the effect that this can have on your shooting at longer ranges.
Where Coriolis requires a bigger correction, though, is with artillery, especially long-range naval artillery, because the snipers are firing at a distance typically less than 2 miles, and the bullet's flight time is then only a couple of seconds, whereas a naval gun fires dozens of miles, and the shell can take more than a minute to reach their target. And for this, Earth's rotation is much more of an issue. Because when you're shooting at something, you're not really aiming for where the target is, you have to aim for where the target is going to be when the shell arrives at that distance. Obviously, for a stationary target, that's pretty easy. But if you look at anything like clay pigeon shooting, they don't aim at the target because by the time that the shells have reached that distance, the target's already moved. So instead they have to lead the target. And naval gunnery does exactly the same thing. When engaging any enemy vessel, that vessel is typically moving, so gunners don't aim for where the enemy is, they aim for where the enemy ship will be when the shell arrives. For this, they need to know the range of the enemy, to know how long the shell is going to take. They need to know the speed and the heading of the enemy to then work out how far relative to the ship's current location will they be when the shell lands. But then the gunners also include correction for Earth's rotation. For example, here is a correction table for the US Navy's 8-inch naval guns, which were used extensively during the Second World War. And we can see there's numerous variables to factor in, such as latitude, what direction the ship is from you, and what distance you are then firing, to then calculate the amount of correction for Coriolis. So a ship at the equator, at 0 degrees latitude, shooting at an enemy ship that's on a bearing of either 90 or 270 degrees, which is straight east or west, doesn't have to apply any correction. However, if you then shoot at an enemy that is 30,000 yards on a bearing of either 0 or 180 degrees, which is straight north or south, then you have to apply 42 yards of correction. And you can see positive correction values are to the right, whilst negative ones are to the left. So if you're on the equator and you're shooting at an enemy that is 30,000 yards north of you, then you have to aim 42 yards more to the left, whereas if you turn and face an enemy that's 30,000 yards south of you, then you have to aim 42 yards more to the right. And the deflections increase the further from the equator, such as at 70 degrees latitude, the deflections can reach up to 155 yards, which is 141 meters. And it was even more for larger guns with longer ranges. For example, the 8-inch guns at 30 degrees latitude could reach 30,000 yards and needed about 112 yards of correction. The 16-inch 50 caliber guns that were used on the Iowa class battleships could shoot up to 42,000 yards, and at that distance they could need up to 196 yards of correction at 30 degrees latitude. For context, a Japanese World War II destroyer like the Kagero class were about 118 meters long. So the amount of deflection that is being applied to some of these shells is longer than some of the ships that they were shooting at. So if the corrections were wrong, the shells would completely miss. Now, obviously, most people aren't really going to be impacted by Coriolis in that sort of a manner. But Coriolis does actually have an impact on everybody's day-to-day life by its impact on the weather. The most striking example of this is probably hurricanes and cyclones, which are basically large rotating winds. Now, hurricanes occur in the northern hemisphere while cyclones occur in the southern hemisphere, but they're essentially the same thing, they just differ on location, and hurricanes always rotate counterclockwise while cyclones rotate clockwise. And this is due to Coriolis pushing one side of the weather region faster than the other. If we take a weather region and we say one edge is near the equator, where the Earth's rotating at 1,000 miles an hour, and the other edge is where the Earth is rotating at only 500 miles an hour, then the center would be moving over a region of Earth that's roughly 750 miles an hour. So we have one side that gets pushed faster and so moves ahead of the center, while the other side is getting dragged behind, and this gradually causes the weather pattern to start rotating. Now, Coriolis not only drives hurricanes and cyclones, but interestingly, it can also stop them, because it drives them by having one edge of the storm at a latitude that's rotating faster than the eye, and the other edge at a latitude that's rotating slower than the eye of the storm. But if the eye of the storm is on the equator, then both edges would now be going slower than the center, and that causes the storm to actually dissipate. It's why you don't see hurricanes and cyclones crossing the equator into the other hemispheres. So, hopefully that clears that up. As always, feel free to leave your thoughts in the comments down below. If you enjoyed this video and you haven't already done so, then please do consider hitting the like and subscribe buttons, and hopefully we'll see you in the next video.